Yanir Rubinstein from Stanford University, and his talk will be on Ricci flow and completion of the space of Kahler metrics.
Well, thank you very much, Mr. Block, and the organizers for having me here in this wonderful conference, and it's really inspiring to be here in this great center, and also this celebratory day. So thank you. So okay, so this is joint work with Brian Clark, my colleague at Stanford. So usually, sort of in many talks I've given, I start with this picture here. So okay, MJ is Kahler, compact Kahler, and so we have the space of functions, and then we have the space of Kahler metrics, and then I say that this has a Riemannian structure, which is called the Mabuchi metric, which is just given as follows. So, as you all know, just the L2 inner product on the level of Kahler potentials. Okay, so, but today I want to talk about sort of a different metric that you can put here, and the idea is, well, you consider the space M, which is a larger space, which is the space of all Riemannian metrics. So this is sort of a huge space compared to H, and I don't know how to draw this, but something like that. And H is a submanifold here. And on this space M, we have the Eben metric, so also called L2 metric. Okay, and so here you look at tangent. So here, of course, tangent vectors are functions. And here, tangent vectors are sort of symmetric 0-2 tensors. Okay. And then here, the metric is defined. So if you take the G trace of these two tensors. Okay. So so this is a perfectly well-defined metric on M, and so there's no problem to restrict it to the submanifold. We get a metric on H, and so we can study the geometry that it gives on the space of metrics. So now, I guess I turn off the light, and so there is this just sort of two-minute. Okay. Okay. All right. Okay. So that's sort of a 2-minute interlude, which so we go back in time to 1953, when Calabi was presenting 2 talks in the AMS meetings in Baltimore. Okay, so basically it's sort of just mind-boggling to me how he sort of in these half a page sort of completely visionary notes just sort of spell out basically sort of the main topics of this conference that is happening almost 60 years later. So in this first talk, he describes his Calabi conjecture, which is stated as a theorem, and then, well, he states this theorem because actually he would like to apply it to understand the geometry of this space H endowed with a certain metric. And that metric, which we call the Calabi metric, is nothing but just inducing this Eben metric on H. Okay, so this is not my idea, this is Calabi's idea, but sort of has gone unnoticed for many, many years. So, and then what he says is that using this Calabi conjecture, we actually see that this induced geometry here is nothing but a sphere. So it's a sphere of constant curvature, constant positive curvature. And what he says here, if you see the last few lines here, he says that, well, the unique geodesics of bounded length between any pair of points. And the last sentence is, he says that the completion consists of the positive semi-definite Kahler metrics defining the same class. Okay, so that's sort of the sentence I want to try to understand today. Okay, so this sentence really sort of sort of been on my mind since I ever saw this this note years ago, and I never really understood it. And actually, there's another note here which I skipped, and in that note he defines the extremal metrics and sort of explains that an extremal metric will be obtained when this scalar curvature vector field is holomorphic. So basically, sort of all the topics of this conference are already spelled out there. Okay, so let me just write this as a question then here. So this is sort of the question I want to understand. So what is the completion of H? And here I'm going to put Calabi's metric, so I'm going to call this GC. So this is Calabi's metric. And so how am I going to define this Calabi metric? So
like in H here, you always mod it out by the constants?
No. But in this metric, we'll see it sort of gets mod out naturally. So here, again, we have two tangent vectors, and the metric is just this. You multiply the Laplacians.
Yeah, so the point of the question was that's not a metric on the space of functions, right? It's only functions by constant.
Well, you can also define it on the space. Just distance in the fibers. Yeah. Right. Okay. So that's the first question I want to discuss, and so sort of the first sort of very elementary observation due to Calabi is that, well, if we just look at this embedding of H into M, here we put the Eben metric. Well, then if I just pull back this Eben metric, I'm going to get twice this Calabi metric. So there's this constant floating around, and it's really just sort of an integration formula. So you can either just look at the full L2 norm of the 1-1 forms, or you can look at the Laplacians. It doesn't matter. Okay, so that's the first question, and so then sort of and two other questions that were on my mind sort of ever since I've seen this note of Calabi is, well, so what is the relation between so this metric completion? So I'll just write a line over a bar over. This is going to denote the metric completion. And sort of stability. And sort of related question is the same. What is the relation between this and Ricci? Okay, so that's what I want to talk about today. So I guess the first thing that comes to mind, so sort of en route to sort of answering this first question, is, well, we have sort of this huge space M, and here we have our H, and so in Kahler geometry we are interested in sort of defining distances between points, distance between Kahler metrics, and sort of a lot of work has gone into understanding the Mabuchi metric. And so here we sort of have another metric, and you can somehow just hope that this distance function you get here might be interesting or not. But anyway, something you want to understand. So one thing you can do is you can because of this picture here of this embedding in a larger space, you can also define sort of a third. So let me just write this. So dm will be the sort of Mabuchi distance, which I'm not going to talk about at all in this talk. Okay. Then there's the Calabi distance, which just And then, so there's a third distance you get from this picture, which is just connect the 2 points by a geodesic in M, an extrinsic geodesic. Okay, and so there's also like a third candidate, so that would be the extrinsic distance.
And distance.
Which, yeah, so I'm going to denote this by dE, which is also extrinsic, also evident in this particular line. Okay, so the first sort of observation, which is not difficult, is that actually, so this Calabi distance and the Evan distance are actually equivalent on H. So let me just write it this way. So So in essence, you don't get any new sort of distance function from looking at this embedding in a larger space. But the reason actually that I want to state this result is just because it's going to be just useful for some remark I want to make at the end. So this way. And so actually this constant you should all know it is just 1 over square root of 2 because well we figured that if I put here H 2GC, then this is just an isometric embedding. Okay, so this just states that the extrinsic distance is always less than the intrinsic one. And so the non-trivial part is here. And sort of just to give an idea of how you show this, well, there's this sort of canonical way to think about M, where you decompose it into a product, which I'm going to denote this way. So here are all the metrics with volume form equal to mu. So mu is some fixed volume form, and this is just the space of all volume forms. And so on the level of tangent vectors, you get an orthogonal decomposition with respect to the Evan metric here. And so you can actually sort of take a path, sort of take an extrinsic, you take 2 Kahler metrics, then you want to look at the extrinsic path that is connecting them, and you want to actually show that this path is not getting too short. Okay? So it's sort of in infinite dimensions, you don't really know that this won't happen necessarily. So somehow it might be that this H is sort of curved in some funny way and that you sort of have long intrinsic geodesics and sort of really short extrinsic ones. So you want to rule that out. And then you just use this decomposition. And because it's orthogonal, well, you can reduce the problem basically to understanding. So let me just define another subspace here. So V inside V tilde. So these are just going to be the volume forms which have volume V. So fixed volume V. So why am I defining this subspace? Well, so this is exactly where sort of Calabi's conjecture comes in. So that was his motivation. So in order to compare extrinsic and extrinsic distances in M and in H, I'm just going to do the comparison between extrinsic and extrinsic distances of V as a submanifold of V tilde. Okay, so that's going to be enough. And for this, well, you actually need this Calabi out here, which tells you that you have an isometry between Calabi space and the space of fixed volume forms where you put the metric sort of the natural L2 metric. Okay. So these tangent vectors are just 2 n forms which integrate to 0. Okay, so this is one way to think of the Calabi out there. Okay, so let me just write what I was saying to prove this theorem. And this is actually not difficult to do. So that's basically how you prove that.
Somehow you have to inject the space of volume forms into the space of metrics, right?
This V tilde.
Yeah.
Yeah, that's right.
So
Yeah.
you have to fix a metric and then use it all its conformal changes.
That's
to do
right.
that?
Yeah. Yeah. So I didn't write this here, but sort of the way you identify an element here with an element here, right? So you would take here some metric, and here you take some volume form, and then you sort of send it to G times mu over E to 2 over the dimension. So.
But for the Kahler story, you're using the Calabi projection, so it's given the volume from the Kahler metric in the class.
Right. So actually, I wanted to say just one word, which I thought is that, well, why did Calabi actually? So it's sort of interesting to see it just from maybe even a historical point of view, like what application Calabi might have originally had for defining this conjecture. Well, so if you just look at the Euler-Lagrange equation of the metric I just erased, of Calabi's metric, well, that Euler-Lagrange equation looks quite nasty, and it's the following. So,
So this is the GD's equation written.
that's right. So that is the geodesic equation. Thank you. Okay, and so that's actually what you get if you do a variation of this energy. And so go ahead and try to solve this equation. But what Calabi observed is that if you write F equals omega phi, so this ratio of volume forms, well, then this equation simplifies a lot, and it just becomes an ODE. Okay, so sort of miraculous, but so. Okay. And just sort of to complete this sort of preliminary stuff. So if we think of this decomposition of M, we sort of have here the V tilde direction, which is sort of isomorphic to the conformal class. And here we have the sort of traceless direction, where we just fix the volume form and change the conformal class. And in fact, what's true is that the space of Kahler metrics sort of it sits at a fixed angle with this, with each conformal class. So and this angle only depends on the dimension. So in dimension 1, it just sits inside a conformal class always, and in dimension 2, it's exactly 45 degrees, and so on. So that's just.
In this equation for F, V is a constant there?
V is the volume. Yeah.
So it's a number.
That's right. Okay. So. good. So we're very close to answering question 1. This point. So now you see, using this isomorphism, well, if we want to understand this completion, it's just the same as understanding this completion, at least abstractly as metric spaces. So what is going to be the completion of fixed volume forms with respect to this induced matrix GP? So
You know, if Calabi had proved that the map from metrics to volume forms was injected by this time?
yes,
So he'd already done that.
we already
part.
done that. Yeah.
So that's already a big step. You know, when you make this change in coordinates, it's sort of,
Right.
the only problem is maybe you go off the.
Right. And sort of an amazing thing is that actually, sort of for some of the things I need today, I don't need this rigidity. So, but sort of it's just nicer to have the isomorphism. But I don't actually need Calabi theorem for everything. So anyway, but so this theorem I just stated as a theorem, even though it's not very difficult. So what is this completion that I was asking about? So this is actually quite simple. So this is, well, how should I write this? Okay, so the completion is really just the L1 completion on the space of fixed volume. And it's not surprising at all, because when you write down the distance function explicitly for this, you see that well, what comes in is sort of the square root of this volume ratio f, and then since this turns out to be a sphere, it's actually sort of isomorphic by the map which takes a function to its square to just the usual sphere in L2 of functions. And so then the completion of that thing is definitely an L2 completion, but then you go back and take a square root, so you're going to get an L1, and you just have to make sure that sort of all these identifications work rigorously. It's not hard. So, but this still doesn't answer.
But question. So M itself wasn't complete.
M?
M.
The script M?
Yeah.
Right, it's not complete.
So you just left it.
So, let me just, like a machine, yeah. So, okay. So, M is not complete actually, but.
You're leaving it when you do this.
Well, here I'm just thinking of V as a submanifold of V tilde. And looking at the completion there. And then, so here I'm not even looking at metrics, I'm just looking at volume forms.
So what is DV? You have
So-
a DE and a DC.
Yeah. So, wait, did I erase that? So,
It's up here at the top of this board. So you call it Calabi distance.
oh, so I defined a GV at some point. Yeah, so DV is the metric,
From there.
is the metric in this one.
I mean, because if you're saying this is the metric completion of this guy, then it's the metric completion of HG6.
That's right, just
So you just
abstractly.
left M.
I did it, leave M, but I'm in the completion of M, I guess. Which, this is sort of this is something my co-author actually studied in his thesis, was what is the completion of M. So, but anyway, it's not needed here at all. Just if you're interested. So, okay, so here, let me just say, just to get a sort of obvious thing to say, but so what is the notion of convergence in this metric? Well, so this is UK converges to mu if and only if these integrals UK minus mu go to 0. Okay, so that's what I mean by L1. Okay, but as I said, this still doesn't answer the first question, and that is what is the completion, because, well, it tells me abstractly what it is, but I want to actually know what it is on the level of metrics, so, or Floris of harmonic functions. And so here, luckily, there was no work needed except reading some very important papers by Dinev and Gedzer, yeah. Okay, and so let me state their results. So, okay, so what they basically proved was, well, you see, in essence, before you take the completion, you can just use the Calabi-Yau theorem to identify volume forms with metrics. When you take the completion, naturally, you would want a generalization of Calabi-Yau theorem, and that's precisely provided by their work. So, and actually, their result is sort of stronger than what is needed here. So, I'm going to define this class E, which was introduced by Gedzer-Yaki, and it's reminiscent of some classes defined by Segrel in the CN sort of local setting. So here, I'm going to so this is inside the space of PSH functions, and it's defined in the following way. So you look at integrals of the Mongeon pair, but truncated. So instead of looking here at phi, I'm going to look at max phi and minus j, and I'm going to integrate over phi bigger than minus j, and this should be equal to just the total volume. Okay. So you look at your function, this function phi, it might have a locus where it's minus infinity. That's the main problem. You truncate it at minus j, and then you just hope that most of the volume is concentrated on the set where it's not going to minus infinity. And then you say it's in the class E, so it's an acceptable function. So for
This is a bit redundant since you're integrating over phi bigger than minus j, you might as well leave off the subscript.
But he wants to emphasize that he's avoiding the very negative values.
yeah. So the point is that, well, the Mongeon pair of such functions just does not charge so-called pluripolar sets, where the function, so the pluripolar sets are the function, the sets. So A is pluripolar.
Because on the set where they are equal, where phi is
Yeah, actually,
minus
right. That's when you get a lot of
you could
contribution.
add some mass
Yeah,
and
right.
you
Well,
want
he's
this
not
must
integrating over that set.
Yeah, that's right. So the point is that the mass which stays at the set, at the level set, goes to zero. When j goes to minus.
This is still a wild point. It's the way it's written, it's the same thing.
Yeah.
Okay.
It is redundant. Because on that set, max of phi minus j is phi. That's all it's saying.
Okay, so
But it's not.
you don't need to put max there.
Right.
So thanks, Sam. So A is pluripolar if A is contained in the minus. So if it contained in this minus infinity level set of some PSH function. And this class precisely functions whose Mongeon pair does not charge any pluripolar. But anyway, I'm no expert on this. So better to look at this. So the point is that, well, by Gedzer-Yaki, you can actually define the Mongeon pair on this class in such a way that it's continuous under decreasing sequences. And this sort of trying to find a domain on which Mongeon pair can be defined in such a way continuously. It goes back to Bedford and Taylor, and since then many others have studied it. But in this context of a Kahler manifold, things turned out to be a bit different, and this was shown by Yeah, so more Jean-Pierre operator. E, and then the theorem of Nina and is, well, that's, if we let mu be negative, I'm not sure. M, then there is this unique phi and epsilon and E such that it's one ampere is equal to this measure. Okay, so and so
Put no mass on critical stuff.
yes, sorry. Too excited. So, should have used the PowerPoint. Yeah. So that's the theorem. This generalized Calabi-Yau theorem, and now let's go back to this statement here. We take an element of the completion. It's a volume form which when you write the volume ratio, it's a density in L1. Okay, so it's absolutely continuous with respect to this fixed measure. Clearly, it doesn't charge any Lebesgue null sets, and actually, in that, then it's not going to charge any pluripolar sets as well. So pluripolar sets are actually contained in conventional sets. So as a corollary, we can just answer this first question. So this is the first question, and then just. Okay, so this is what the completion is. Okay. And I would like to just say here that this subset, this class here is actually a strict subset of E, and this was in some sense alluded to in Courvoisier's plot. So there are actually measures which charge Lebesgue null sets, but these won't be pluripolar sets. So then this class is certainly larger than this class. So So now I want to move on to the second and third question. All right. So is this metric completion good for anything? That's basically what we want to see. And so here I want to state this, not state, just remind everyone. This white Yau-Tian-Donaldson conjecture, which just say that, well, Kahler-Einstein in this setting, or at least in a specific setting, so it says that the Kahler-Einstein metric should exist if and only if some stability holds. And so the conjecture is actually leaves you the possibility of choosing your notion of stability. So that's a part of the game. So so I decided to play this game, and so here. So here I should say that there are actually sort of two sort of types of notions that you could study. So one would be analytic, and one would be algebraic. Okay, so I'm going to stay on this side and not actually say anything about the algebraic notions, which we heard in very interesting talks already. And so what kind of analytic notions of stability are there out there? So the first one is due to Tian, and what it says is that, well, Kahler-Einstein is equivalent to properness of Ricci energy. So it's fundamental and hard result, and this was sort of later extended by Song-Weingrove, I guess 2006 maybe, to another functional defined by Chen and Tian, and later I also extended this to sort of this Chen-Tian functionals into up to the end, but then you have to take the properness on the subspace, so there has to be the space of positive Ricci metrics. Okay, so this is just y, and then there's a second sort of very interesting and enigmatic notion defined by Donaldson, which is sometimes referred to as geodesic stability. Yeah, so let me state his conjecture. This acronym was already used in one talk. So the Noguchi energy, I'm going to denote this by E0. Okay. And third point is that this such animal okay, so the conjecture says, well, that if you don't have a constant scalar curvature metric, then there should be an analytic way, sort of an analytic one-parameter subgroup that destabilizes the manifold. So that by that he meant an infinite geodesic ray along which the K energy is decreasing one as well. And then once you have such one such geodesic, you should have one emanating from any point in space. So let me make a definition. So I'm always going to restrict to final manifolds. To the Kahler-Einstein case, and then you say that MJ is Calabi Ricci unstable. So it exists Ricci flow that diverges. So that diverges in the metric completion. Okay? So otherwise, it's a state. Okay? So,
I thought that Mr. Buck was inside with French.
really? Oh, no. Totally coincidence, actually. Yeah. Okay, so one.
You consider it stable if the geodesic lands on something in closure.
In the completion.
You get something, one of these funny things that you can erase.
Contained in that class. It's contained.
Right.
Right.
So that's still stable.
That's this. So, yeah, so I'm going to draw a picture in a second, but I want to say why I wrote down this conjecture of Donaldson. Well, because basically I've been thinking about this conjecture for some years and don't have really an idea how to prove it. But then I realized there's sort of a much easier, well, it depends. Well, it actually uses some machinery, but sort of an easier notion of stability that you can get, which is very analogous to Donaldson's notion. Okay, so why am I saying that? So the first thing to note is that, well, the K energy is monotonely decreasing along the Kahler Ricci flow. So forgive me, but I always say Ricci flow or Kahler Ricci flow. I always mean the normalized Ricci flow, which is just the Kahler Ricci flow in the final set. Okay, so just like what Donaldson required for this destabilizing geodesic, the Ricci flow automatically has this property, and actually, the other thing is that in the definition you can replace diverges in its completion by has infinite DC length. Okay, and so the unstable situation is exactly, well, this will follow, so this actually follows from the proof later, but an unstable situation is exactly when you have a Ricci flow that has infinite length in this metric space. Okay, and that's sort of precisely an analogy with the conjecture itself. Okay, so this definition motivated by this result, so
Of course, you're always taking the Kahler class if you see one.
yes, oh, thank you. Okay, so this result just says that, well, what we expect to happen for the geodesic stability, according to Donaldson, actually is true for this sort of Calabi-Ricci set. Okay,
So the point is that the second thing is no matter Your initial statement was that for some initial data it diverges, but you're saying if it does, if that happens,
Right.
you're running measure.
Exactly. So that corresponds to just sort of the second and third units. So that really I stated just to make the comparison, because anyone who knows the proof, well, it doesn't matter what initial data is. All right. So the point of this theorem is actually so the main ingredient here is actually understanding the blow-up locus of solutions to the Ricci flow when there is no Kahler-Einstein metric. So sort of this classical work of Tien and later Nadel that shows that, well, if you try to produce a Kahler-Einstein metric and the continuity method fails, then you actually can take a subsequence and of Kahler potentials and that they blow up along a certain subvariety in there. Okay. And in fact, actually, if you look at these papers, then you see that, well, actually, not only does it blow up, but also the volume form sort of concentrates more and more along this subvariety. Okay. Now this is all for the continuity method, and actually, in a sort of earlier observation I made is that a couple of years ago is that, well, these arguments for the continuity method, they carry over to the Ricci flow, given sort of this huge amount of work that has gone since Perelman's breakthrough. Okay, so basically, the idea is that, well, if you don't have a Kahler-Einstein metric, then you prove a certain Harnack inequality, and that tells you that, well, relying on this fundamental work of Tien in Nadel, that you actually get concentration of the volume along this set, where actually the Fourier harmonic functions are going to minus infinity. So we have really an opposite situation, sort of a limit which is opposite from being an E. Actually, all of its mass is being concentrated on a pluripolar set. Okay, and so basically the idea is that then the Kahler-Ricci flow has a subsequence which converges to something outside of E, this sort of type of Getz-Zariaki class, and then if it does so, then of course the flow itself cannot converge into completion. So the picture to take from here is that, well, you have and so this is something that always confused me. So and I think I even once gave a talk where I drew the wrong pictures. So I didn't know. So let's say you're in the situation where there's no Kahler-Einstein metric. Okay, so what does the Ricci flow do, right? So one thing it could do is it just go to the boundary. Right? That would be one situation. And another situation would be that it just sort of spirals around and doesn't converge to anything. And so basically what we see is that this is what happens. This doesn't happen. Okay, and then the same, of course, holds for the continuity method. Yeah. So that's,
H is bounded.
sorry?
No, H is bounded.
What do you mean, bounded in what sense?
Bounded as it is a diameter.
Well, yes, so that's a confusing thing, right? So actually the diameter of H in this Calabi metric is finite. That's right.
It is.
It is finite, but that's not true for the Mobushi metric. So you know, that's why I always thought the Calabi metric has really no substance and no application, because it's sort of a bounded set. So nothing really interesting can happen. But then if you, instead of geodesics, look at Ricci flows, then you get something which is to me interesting. So let me know. Is it 5:22? Yes. So almost done. So I just want to state sort of another result about the convergence of the Ricci flow, which really just follows from the proof of the previous theorem. So if you assume the Kahler-Ricci flow DC converges, so converges in this metric sense. So, i.e., the volume forms converge in L1, then actually the same reasoning shows that then the Kahler-Ricci flow converges smoothly. And smoothly, as good as you want, so exponentially. Okay, so in some sense, really weak control for the Kahler-Ricci flow already gives you sort of the best control you can hope. And here, the point is that I'm only saying L1 and not any LP bigger than 1, because as we heard in several talks, the Kovogia's work would already give you a C0 estimate if you had LP control. But here, sort of the borderline case, you're just assuming L1, and then you already get a C0 estimate, and then work with other people. Chen, Tian, Perelman, Fong, and his workers gives you the rest, sort of from C0 to the higher estimates. So there's another corollary.
Wait, how do you get from L1 to C0?
Exactly. So that's exactly the point. So that's sort of by this sort of mechanism of ruling out. So you assume that you have no C0 estimate, then that means you will also have no higher estimates. So then you will have no Kahler-Einstein metric, and then you're able to construct this sort of subsequence which limits out. And maybe I just state another corollary, just to sort of show there is some application. So here, if you define this to be the scalar curvature along the flow, then the Kahler-Ricci flow will converge if and only if. So here you look at this L1. So this. Okay, so this just gives you an analytic criterion for when the Ricci flow converges, and the point is that sort of the previously known bound was here you replace L2 by C0, which is weaker, but really sort of this sort of explains where that kind of estimate comes from. You really should just think of the Ricci flow as living on this metric space, and this then just corresponds to the length. So if it's finite, you have finite length, you have convergence. So just I may make a remark for people who might be interested. So the first theorem I said showed you that it said that the extrinsic distance, the Eben distance, was equivalent to the Calabi distance. Okay? And so this notion of stability here is actually just a Riemannian notion. So it's just actually defined in terms of the Eben metric on the space of all metrics. So then, since the Ricci flow also can be defined on that space, it's interesting. Maybe there are sort of Riemannian analogs of these results about convergence. But I have no idea. So let me just stop. Oh, yes, and actually, I don't know. I don't have a question, but it's sort of embarrassing that I wrote here that, but I forgot to mention this. That there's this very nice article of Kalamai, which describes these results of Calabi. So it actually appeared last year. It was one of the sort of reasons I came back to think about these problems. But so there you can find a lot of the details and more things about Calabi's construction.
Questions?
Is Ricci flow some brilliant flow
Well, I guess if you look at if you look at derivative of K energy, you have this thing here. So, and then along the Ricci flow, you have this. So in that sense, it sort of decreases Mabuchi energy. But I don't know if this answers. So I haven't been able to show that, let's say, distances between points decrease under Ricci flow. Like, so there's a result of Calabi and Chen which shows that for the Calabi flow, but I don't know how to show this in this sense.
That is the test for stability of definition.
That's right, yeah. It doesn't see. Yeah. Maybe there is. Yeah.
So there doesn't really seem to be any way to push this, unfortunately, if you're not in Banno case.
So actually, there is sort of a hopeful way that you can define sort of analogs of Ricci flow where but there's no there's no technology really available. I mean, you know these kind of flows where you look at the harmonic Ricci and sort of just theoretically it might be, but right. Yeah.
Can you discuss the report just one more time?
Yes. So
You assume on contradiction that it doesn't go smoothly?
yes. So it does not converge. Then that means you have no C0 estimate. Okay. And so once you have no C0 estimate, then you can take a subsequence where sort of the C0 norms are going to infinity, and then you sort of you have a Harnack inequality nevertheless. So that shows you that sort of it's going both to minus infinity and plus infinity. In a certain rate, you normalize the function to be just completely negative, and then you actually construct a certain multiplier ideal sheet with a certain exponent. And once you've done that, the PSH function which defines this sheaf is actually not an E. And so you're done.
Is there any known example where you have any metric defined on these spaces where Taylor-Ricci flow converges in this metric, maybe much weaker than this, but not Taylor-Ricci stuff?
So another metric on H.
Does it ever converge? Maybe different completion, but not Taylor-Ricci stuff.
That's a great question, but I just don't know. So you would probably want maybe stronger metric. Or a weaker one. But yes, so from Mabuchi, I don't know.
Can you get canopy bound directly from the CR? Actually, that's to show that if no matter where you start, the killer is pushing 0 to 0 or something. I guess that's the conclusion.
So you want what do you want to assume?
Your CR stability.
Just assume it's stable.
Don't use the metric and get it, and just go directly CR stability to a lower bound and presumably easier than getting kilohertz.
Maybe. Yeah, we talked about that. I mean, so without using parallel, maybe I don't know.
Well, the amount is saying that the kilohertz will just under this hypothesis push the Canage map and apply to the kilohertz will just go always to 0. I guess that's the conclusion, right?
Right, it goes to the kilohertz.
You know the derivative is negative, but you don't know that it's necessary.
Right. You don't know, like, when you integrate, you get.
Well, let's thank our speaker again.